problem, let's look at another case. Using integrals to find consumption over time. It looks like a lot, but let's just walk through it. It's a lot simpler than it seems. The rate of consumption of oil in the United States during the 1980s in billions of barrels per year is modeled by the function C equals 27.08 times e to the t divided by 25, where t is the number of years after January 1st, 1980. Find the total consumption of oil in the U.S. from January 1st, 1980 to January 1st, 1990. So to solve this, we're actually just going to make this into another integral. Hold on a second. So, once again, I'm going to write out that we know that C equals 27.08 times e to the t over 25. Once again, to find net change, we know that all we have to do is find the antiderivative of it, or use the integral. So we're going to set up our integral from 0, which represents 1980, to 10, which represents 1990. Then we are just going to plug in this formula for C, which is 27.08 times e to the t over 25 dt. Now this one is a very complex antiderivative, so we are not going to use antiderivatives. We are going to again use nderive, or math option number 9. I mean not nderive, function integration, sorry. So from 0 to 10, 27.08, and you should be following along as well to make sure you get the right answer, times e to the t over 25 dx. And you should come up with the answer of approximately 332.965 billion barrels. As shown on the calculator. Last, we are going to wrap up with one final example. A car is moving with initial velocity of 5 miles per hour, accelerates at the rate of a of t equals 2.4 miles per hour per second for 8 seconds. So we're going to first find A, how fast is the car going when the 8 seconds are up, and then find B, how far did the car travel during those 8 seconds. So let's look at A. So we know that A of t equals 2.4 t. So first we need to find V of t. The formula for V of t. And by doing so, we are going to have to integrate again. So we're going to find the integral of 0 to 8 of 2.4 t dt. And by finding this is not going to find our final answer. This is only going to show our net change of velocity. So make sure we don't forget to add it to our initial rate. So when we integrate this, which you can integrate on your own using function integration or the use of antiderivatives, and we're going to find that the net change is 76.8 miles per hour. But note that this is net velocity. Not the final answer. And so what is our initial rate? It tells us in the beginning with initial velocity of 5 miles per hour. So next, simply define V of 8. We are just going to add 76.8 plus 5 to get our final answer of 81.8 miles per hour. And that is our final answer. This is a good example of how we can return to find the function of velocity from if we know acceleration. Last, we're going to take a look at how far the car traveled during those 8 seconds. So first, we need to find the actual formula for v of t. So we're once again going to integrate acceleration, except this time we're going to use an indefinite integral rather than plugging in the 0 and the 8. So we're going to do the integral of a of t dt, which equals the integral of 2.4 t dt. When we use antiderivatives, we find that v of t equals 1.2 t squared plus c. So next we have to focus on finding the c value. And we think, how would we do this? Well, there's a simple way. We know one value of this function, that when when time is 0, velocity is 5. So we are simply going to plug in this point to the function. So we're going to set, because we know that this is the x and the y, so 5 equals 1.20 squared plus c, and solve. So c equals 5. So now we know that v of t equals 1.2 t squared plus 5. But yet we still don't have our final answer of how far the car traveled during those 8 seconds. So next, we are going to relate back to the distance formula that we used before, which is taking the absolute value of the displacement. So we are going to set up a definite integral from 0 to 8. Don't forget the absolute value sign, because that's very crucial for finding distance, of 1.2 t squared plus 5, which is a v of t dt. And when we solve this, using either, once again, antiderivatives or function integration, we find that it equals 244.8 miles per hour times seconds. Now these units are what, we cannot leave our final answer in, so we need to change the units. So to do so, we know that we have miles per hour times seconds over nothing. And we want our final answer to be in miles because we are looking for distance. So to do so, we need to find a way to cancel out hours and the seconds, because we only want to be left with this miles right here. So to do so, we are going to multiply by hours over seconds. So to do this, we are going to multiply. I'm running out of room here, so I'm going to add another sheet of paper. We know that 244.8 is the miles per hour. So we can leave this representing this miles per hour right here. Times, now we need to multiply by the hours over seconds. We know that there's 3,600 seconds in an hour, so we can multiply this by 1 over 3,600. And by doing so, we are left with the final answer of 0.068 miles. And this is our final answer for total distance. So we figured out this problem as well. Nice job. And so that sums up our lesson. And so we are left with our assignment for tonight. Oh yeah, it's going to be really fun. It is page 386, problems 1, 3, 9, 10, and 22. And you can try to use the book for help for the first couple, but you should be able to get them. They go right along with the examples, and feel free to watch this as many times as you'd like. So, thanks for watching. And hopefully you got something out of this. Thank you.